Okay, so this E part is basically just an algebra question. It's a manipulation of formula question, but I thought we'd have a little look at how they've derived this formula for the curved surface area of a cone in terms of its radius and its vertical height, h. We'd be used to seeing the formula for the surface area of a cone in terms of its radius and its slant height, L. So this measurement here. So the curved surface area of a cone is pi times r times L, and they want us to view this formula in terms of r and h. So how did they get there? So if we have a look at a cone, we can see that there's a right angle triangle in a cone here that's made up of a hypotenuse of L and two sides h and r. So if we use Pythagoras' theorem, we can then express L, the slant height, in terms of the h and the r. So we have L squared is r squared plus h squared. L then is the root of r squared plus h squared. And then we're going to take this value of L and put it into our formula that's in our maths formula book for the curved surface area of a cone, pi r L. So we're replacing the L with the root of r squared plus h squared. And that's essentially what's been done for us already. So we have a derivation of the formula that we'd be used to using because they want us to use the letters r and h. Okay, so that's the setup of it. We weren't asked to do that in the question, but like that, it's interesting to look and see where it came from. And a lot of the question 9 was this idea of using formulas that have been derived for us from formulas that we would be used to seeing in our maths and formula book. Okay, so let's go and we're going to try and rearrange or manipulate this formula so that we make h the subject instead of s the subject. So how do we go and do that? So the idea with a manipulation of formula question is we can do anything we like to one side as long as we do it to the other side. So if we start with s is equal to pi r on the root of r squared plus h squared, have a quick look at what we're trying to isolate. We're trying to get the h on its own. Well, the first thing we're going to do is we're going to divide both sides by this pi r. So if we divide the left by pi r, we get s over pi r. And if we divide the right by pi r, the pi r cancels with the pi r on top. Okay, the next thing we're going to do is we're going to try and remove this square root. And the way we can remove a square root is by squaring it. So we need to square both sides. So on the left, we're going to square s over pi r. And then on the right, we're going to square the root of r squared plus h squared. Now, when we square a fraction, just to look at this on the side here, so s over pi r, and we're going to square that. What we do when we square a fraction is we square the top and we square the bottom. And if the bottom consists of two separate terms multiplied by each other, each of those gets squared. So that's going to be s squared over pi squared r squared. So that's the left hand side. The right hand side, when we square a square root, it removes the surd and we have r squared plus h squared. Okay, keep thinking of what you're trying to isolate. So we're trying to isolate h. So we're going to remove the r squared from the right hand side by subtracting r squared from both sides. So now on the left hand side we have s squared over pi squared r squared minus r squared equals h squared. I'm going to tidy up this fraction on the left hand side by finding a common denominator. So we might just do this over on the side here. This is s squared over pi squared r squared minus r squared over 1. So if we have a common denominator that's pi squared r squared, well, clearly pi squared r squared goes into pi squared r squared one time, so that's just going to remain s squared on the top. And then 1 into pi squared r squared is pi squared r squared, so we need to multiply that by the r squared, so we get pi squared r to the power of 4. So that's what we're going to get on the left hand side if we find a common denominator and write it as a single fraction. Okay, remember we're trying to get h on its own, so we have a h squared. If we get the square root of both sides, then we'll isolate the h and get h on its own. So square root of both sides, the square root of h squared is h, and then we have the root of s squared minus pi squared r to the power 4 over pi squared r squared. Now, we're very nearly at the finished. We have written h in terms of s, r, and pi, but they want it to look in a particular format. And if you look at the format that they're looking for, they don't have a surd on the bottom. So what we're going to do is we're going to say that the root of s squared minus pi squared r to the power 4 over pi squared r squared, we can separate that into the surd of the top over the surd of the bottom. So the rule of surds means that if you have a surd of a fraction, that's the same as a fraction of those two surds. The top is going to be the root of s squared minus pi squared r to the power 4 still. But then if we find the square root of pi squared r squared, think of the root of pi squared r squared. That's the same as the root of pi r all to be squared. Well, clearly the root of pi r to be squared is just pi r. So what we have is that h is equal to the root of s squared minus pi squared r to the power 4 all over pi r. And that's in the format that we're looking for. So the a, this term here, is pi squared. Now, they don't ask for this, but we may just write it down. So a is equal to pi squared. We have n here is 4. So n equals 4. And then finally, we have that the b is the term next to r. So b is equal to pi. So it's really just a manipulation of formula question. It's a really good one. It asks us to take a lot of steps to isolate the h and write h as the subject of the formula. But it is good to just look and see that sometimes we're given a formula that has been derived elsewhere. And we, like I said, we saw that a lot in question 9. And this idea that when you're given a formula, not to be afraid of it, it's not something that's completely new. It's just a formula that's seen in a way that you wouldn't have seen maybe before.